one last little bit, and then we will go to beta and gamma decay. But the last little bit that you need to know is that the question is why is alpha decay possible? And the general criteria for whether a radioactive decay is possible is that the products have to have less mass than the parent. It has to release energy. Okay, and this is just a natural tendency to reduce potential energy. In fact, this is what is powering the powerful tectonic forces deep within the Earth. Yellowstone, which in 600,000 years ago covered the entire breadbasket of the United States in 8 feet of ash. Okay, Yellowstone is one of these hot spots, super volcanoes, right? This is what's powering that, is this conversion of mass to energy by radioactive elements in the Earth's core. Okay, and the thing you need to know about alpha decay is that it really only happens for very, very large nuclei. You're not going to find carbon and oxygen and all these guys alpha decaying because it's just energetically not possible. But these guys like uranium and thorium and all these guys, right? Those guys are the ones where it's possible to. And the reason that it's possible to is that the helium nucleus is itself very tightly bound. Okay, so if you spit that out, you're automatically lowering the right side, the mass of the right side of the equation, because tightly bound means less mass. Yeah. Here is a chart, and this is a very interesting chart, that all people who want to get energy out of nuclear power, right, look at this chart. This is binding energy per nucleon. So you find the binding energy of the nucleus. You divide by the mass number, and that's what this is, right? Now, what you need to know, Jason Rhoda, is that this number, the bigger that number is, the more stable the element is. The bigger that number is, the more energy per nucleon you need to put in to tear it apart. Now, the bigger this number, the binding energy per nucleon is, the more stable the atom is, right? So, if we look at this thing, the most stable nuclei are what? Iron or nickel, right? Somewhere there, right in there. Iron or nickel, right in the middle of the transition elements, right? So there it is. If you look at uranium-235 has the ability to become more tightly bound. Now, when you go to more tightly bound, you release energy. This is what you're doing when you burn a piece of paper, right? You're turning from cellulose and free oxygen in the atmosphere to carbon dioxide and water, right? Carbon dioxide and water are more tightly bound. You're releasing energy, right? In uranium, you can fission, nuclear fission, which is splitting the thing into parts, right? You're going to things that are more like iron, right? Therefore, you're releasing energy. So what we destroyed Hiroshima with was the potential energy stored in uranium in the Earth's crust, right? We purified it, and then we allowed that to split, and it became something like iron, more like iron. Actually became things like radium and et cetera, right? Okay, now, look at this one. What about this transition from hydrogen to helium? Is that more or less potential energy released? Kind of like a lot more, right? So a far better way to kill people is to use a hydrogen bomb, correct? Hydrogen bombs don't do fission, they do fusion. When you put the nuclei together, that's called fusion. You're fusing them together, right? And so you use an ordinary uranium or plutonium bomb as a fuse, and then you actually get the temperatures high enough that you get the hydrogen to bond with helium. And these are the things that are in millions of tons of TNT, not thousands of tons of TNT explosive power, right? Which is, well, that's the big thing, right? If you could harness nuclear fusion, that would be wonderful. The way we do it with bombs is that we aren't anywhere near it, and we use a actual fission bomb to set off as a fuse for it, which isn't terribly practical in like a small nuclear plant. And so there's all sorts of ways that they're trying to combine it, and they're actually set. I think France has a thing called ITER, I-T-E-R, or something that's gonna hit the break over point where it actually releases more energy than is used to set off the reaction, right? But the practicality, there's actually a real good article in Scientific American within the last year. The practicality of it is way out there, because well, the thing that absorbs the neutrons, one of the problems that we've got is that it's got to generate neutrons, and it's not clear exactly how that would do that in a long-term sort of situation, right? And then things that absorb neutrons tend to like degrade physically because you're changing what element it is. So it's yeah. Here we go. Okay, helium nucleus. There it is. Right? Okay. Now, here's another weird thing about alpha decay, is that alpha particles, when they're released, don't have enough energy to have escaped from the nucleus. And here's what I mean by that. Let's consider the opposite of an alpha decay. For every alpha decay, by the way, there's something called alpha capture that you can make happen, right? To make alpha capture happen, what you have to do is you have to overcome the Coulombic repulsion of the nucleus. So this is my, speeding alpha particle. Here's my nucleus, right? And at low energies, this alpha particle is just simply repelled by the nucleus. Yes, watch this. It's like, right? Because the alpha particle is positively charged and the nucleus is positively charged, yes? Okay, this is like one of those closest approach problems, right? So at low energies, we don't have enough energy. We're always being repelled by the nucleus, right? You have to have a high enough energy, and specifically on this graph, you have to have an energy equal to the height of this thing to get it captured, right? So you have to get it close enough that the strong nuclear force goes, I like that, like this. And this, by the way, you can't tell, there's a hard drive magnet right here. That's the strong nuclear force. Watch this. Oop, not enough. Not enough. Oh, there we go. Just right. Yeah? Okay. That's enough energy to be captured by the strong nuclear force, which is represented by this magnet, right? So we know how high this potential barrier is. Because we've done alpha capture experiments, we know that they've got to have this much energy. Yet when we see these alpha particles, they don't have that much energy. They've got this much energy, yes? They should have 15 or something million electron volts. They come out with like 5, right? So the question is, how did they then escape? Well, if they didn't go over this barrier, what did they do? Yeah, they tunneled through it. Of course, some kid wrote a paper then and talked about how this gradual process, how they sort of bore their way through like a tunnel boring machine. No. It's not this gradual process. It's actually a very rapid one, because what happens is an alpha particle in the nucleus is given, like pure quantum randomness via the Heisenberg uncertainty principle, right? Is given energy that it doesn't have. It gives it back very quickly. But once it gets that energy, it goes over the barrier and then gives it back to the universe. Yeah? So very briefly borrows energy from nowhere, no interest loan, right? And then gives it back. But by the time it gives it back, it's free from the nucleus and it's gone. Isn't that weird? This is a purely random quantum event. A purely random quantum event. It cannot be predicted when it's going to happen, when the Heisenberg uncertainty principle is going to see fit to cause an alpha decay. It just happens. It's random. And not only is it that we cannot predict, it's that it cannot be predicted. There is no hidden variable theory that will someday predict that, right? So all of these decays... Yeah, isn't that crazy? I don't know how you do that, but he did. It's called the Bell theorem. Okay. So anyway, all of these decays are happening at a random interval. This is pure quantum randomness that cannot be determined. And all of them are because of some sort of tunneling event. And that's the only way that the nuclei are stable, is that if you look at them, they're stable. But if the particles inside them borrow energy from the vacuum, as we like to say, right? Okay. Or, in America we say borrow energy from China, right? But anyway, if we borrow energy, right, we can escape, the things can escape, and that's how they can be stable and also unstable, right? It is that they are very nearly have enough energy to escape. They don't have to borrow much to escape from their situation. Crazy, huh? And then we need to change this. This is h over 4 pi. So it violates conservation of energy, but very briefly, yeah? And it's called tunneling, but it's not a gradual thing. Kids want to make it a